नमस्कार. मुंबई विद्यापीठाचे विजयालक्ष्मी विश्वनाथ दळवी महाविद्यालय तळेरे व विश्वभूषण भारतरत्न डॉक्टर बाबासाहेब आंबेडकर महाविद्यालय आंबवडे आणि डोंबिवली शिक्षण प्रसारक मंडळाचे के.व्ही. पेंढारकर महाविद्यालय डोंबिवली यांच्या संयुक्त विद्यमाने खास करून कोकण विभागातील विद्यार्थ्यांसाठी कन्सॉर्टियम व्हर्च्युअल लेक्चर सिरीजचे आयोजन केले गेले आहे. तर जे विद्यार्थी मित्र या लेक्चर सिरीजचा लाभ घेत आहेत त्यांना मी विनंती करते की दळवी कॉलेज यूट्यूब चॅनल ला लाईक, शेअर, कमेंट अँड सबस्क्राईब करा. आज लेक्चर सिरीज मध्ये आपल्यासोबत डॉक्टर किशोर सुखतणकर, गोगटे कॉलेज रत्नागिरी येथे प्राध्यापक म्हणून काम करत आहेत. फिजिक्स विषयातील इलेक्ट्रॉनिक्स या घटकाबद्दल आपल्याला आज ते मार्गदर्शन करणार आहे. तर मी अधिक वेळ न घेता सरांना विनंती करते की त्यांनी लेक्चरला सुरुवात करा.
Thank you very much for my introduction, madam. And this is an excellent opportunity for we people to interact with the students of Konkan area in the pandemic situation where physical interaction is not possible. Myself, Dr. Kishor Sukhatankar, I worked as principal of Gogate Jogalekar College, Ratnagiri, which is one of the esteemed institution, and it has reaccredited by NAC 4 times in an A grade. I served as vice principal of the faculty, vice principal administration, and principal of the college. And I'm very much happy that I'm interacting with you through this lecture series organized for the student of Konkan area in particular. The topic I feel like to deal with you is electrodynamics theory course. The code number is given USPH 504. The learning outcome of this course are displayed right now. To understand the laws of electrodynamics, to understand Maxwell's electrodynamics, to understand how optical laws can be derived from electromagnetic principles, and to develop quantitative problem solving skills. These are different units to be covered in this particular course. Unit number 1 is electrostatics, and unit 2, 3, and 4 are further units to be dealt in this entire course. We are typically related today with unit number 1, which is electrostatics. Now what it contains basically? It contains review of Coulomb's and Gauss law, divergence of electric field, application of Gauss law, the curl of electric field, introduction to the potential, comments on potential, potential of localized charge distribution, Poisson's equation and Laplace's equation, solution and properties of one-dimensional Laplace's equation, and properties of two-dimension and three-dimensional Laplace's equation. So unit 1 of this electrostatics typically continued with boundary condition, conductors and second uniqueness theorem, and finally it is a classic image problem. The reference book for this entire course is David Griffith, third edition, and articles to be dealt with are given in this particular slide. So we begin with the course of electrostatics itself. Basically, why this course is to be necessary for any assigned students to go through? It is because of the fact that the world around may be atomic world to the universe. Everywhere you will find that the systems that are working around, maybe living system, maybe non-living system, wherever you will find that the charges are there. And whenever there is a system of charge, how it behaves, what are its properties, how it affects the nature as a whole, is to be understood very properly. And therefore, the course in electrodynamics appears to be very much important. And therefore, I can say that electrostatics is the starting point of all these things together. If I divide this word electrostatics, basically, you will find that the word statics appears. And it typically indicates that whenever charges are statics, how they interact with each other is basically dealt by this unit or course in electrostatics. Now, whenever we deal with electrostatics, the slide itself shows to you that there is a system of charges. Charge Q1, Q2, up to charge Qi are separated by each other. They are shown as point charges basically. This system is typically known as a system of discrete charges. System of discrete charges. And we call it as a source charge basically. We call it as a source charge. And this source charge will develop electric field around, and to have a feel of this electric field we are placing here what is known as a test charge. So how test charge feel in this electric field is our basic problem, and therefore as we go further and further in the part of electrostatics, basically how this source charge interact with this how this test charge interact with the source charges is basically the thing to be looked upon. Now this another diagram typically shows you a geogrammetric picture of the two charges. This is a source charge Q out of these test charges basically, source charge Q, and this is a test charge. This R bar is position vector of a test charge with respect to the position of source charge. Now, whenever we deal with the content published in the book of Griffith, how this position vector is represented is typical. You know, R is represented in various ways. Fine. But whenever we shows a position of test charge with respect to source charge, this sort of letter is prescribed by Griffith to show the position of source charge with respect to a test charge basically. Now whenever we come across electrostatic as a whole, and typically electrostatics is a region where the charges are stationary, the principle that works around is called as the principle of superposition. Now what is the statement of principle of superposition? It states that interaction between any two charges is completely unaffected by the presence of other. If I go back to my previous slide, it indicates that there are so many charges contained in the source charges, Q1, Q2 up to Qi. And this system of source charge is interacting with a test charge. Now, principle of superposition says that whenever Q1 is interacting with capital Q, that is test charge, this interaction is independent of presence of other charges. Okay, let me go to the next slide. Interaction between any two charges is completely unaffected by the presence of other. Now it is interesting that this principle of superposition apply even to the gravitational phenomena also. So whenever we say something about the gravitational force, it behaves in this manner only. Whenever Earth and Moon interacts, the gravitational law says that it is independent of other heavenly bodies which are around. Similarly, whenever electrostatic force of attraction or repulsion that acts between any two charges, it is independent of charges around. So, when Q1 and capital Q interact with each other, This interaction is independent of whether Q2 is present, whether Q3 is present, or whether Qi is present. Interaction between Q1 and capital Q is independent of the presence of charges around. And therefore, typically, what is F1? F1 is the force between Q1 and test charge capital Q. What is F2? F2 is the force between charge Q2 and test charge capital Q. And therefore, whenever I want to find out F, that is the resultant force acting on capital Q, that is test charge, because of source charges, it says that it is superposition, that is vectorial addition of all these individual forces. So F1 bar plus F2 bar plus F2 bar and so on up to Fi bar. So this vector addition finally determines the resultant force F acting on charge Q because of source charges. And what is the beauty of this principle of superposition? So whenever Q1 and capital Q interacts, the force acting on charge capital Q is F1. It is independent of other forces. And therefore, the final force acting on test charge capital Q can be obtained by simply a vector addition of all these forces together. And therefore, we can find force on test charge capital Q due to a system of source charges. Now, in the real regime of electrostatics, we say that source charges are steady, test charge is steady. What is the situation in practice? In practice, it will never happen. Source charge may be moving around, test charge may be moving around. So, the final force, basically, in practice, in actual practice, it depends on both their velocities. That means velocity of system of charge, velocity of a test charge. What is the acceleration of their motion? So everything will determine ultimately the force on test charge Q because of system charges. But whenever we want to study any complex systems, which is dynamic system, we cannot directly study the dynamic system. We should understand first to begin with. We should understand first to begin with if the charges are steady, basically, if the charges are steady, how they behave. And if I know that if the charges are steady, how they behave, then I will be able to go to the situation where the charges are dynamic. And therefore, first step to start with the study of electrodynamics is to consider source charges are stationary and finally test charges are stationary, and therefore we are in the regime of electrostatics, and therefore word static is important, which indicates that we are dealing with stationary charges. We are dealing with stationary charges. Now this diagram shows you the vectorial representation as accepted by in the book of Griffith. What it shows in a three-dimensional space, this is a source charge, small q. This is, and this is a test charge, capital Q. This is a test charge, capital Q. So how their positions are described with respect to this origin. So in a Cartesian three-dimensional system, what is R bar? So now see how R is represented here and how R is represented here. There are two different ways of the representation as a whole. So what book of Griffith adopts? It adopts that when a position of any point is described with respect to origin, R is represented like this. And whenever position of any point is described with any other reference point other than origin, R is represented in this particular manner. So this is the notation basically adopted by Griffith in his excellent book. So now, what is R bar? It is a position vector of charge capital Q, which is our test charge with respect to origin. And what is R dash bar? What is R dash bar? R dash bar is a position vector of source charge, with respect to origin, Fine. Now, what is the position of capital Q, test charge, with respect to small q, which is source charge? Okay, let me repeat. What is the position of test charge with respect to source charge? It is basically according to a triangle of vectors. It is R bar minus R dash bar. R bar minus R dash bar. And this is described typically as this notation. This is typically shown as this notation, and therefore I am keeping both the figures side by side. So out of this second figure, only one source charge is placed here with respect to a test charge, which may be placed here. This point where test charge is kept, capital P, is called as a field point. And the point where source charge is placed is called as a source point. Now, why typically call this as a field point? It is because of the fact that I want to sense the electric field here. So what is the electric field at field point produced by this system of charges? So what this source charge will do? This source charge will produce electric field around. And what is this electric field at point P? That I want to find out. And therefore my aim is basically to find out the field at field point because of this system of charges. How to accomplish this? How to find out this electric field? Electric field is basically a vector quantity. So therefore it has its own magnitude and direction. This field point will be different in different situations. If I take another field point, electric field will be different. If I take another field point, electric field will be different. So therefore position of this field point will change in the space. Wherever you want to find out electric field, the field point will be set there. The source configuration is stationary. And it produces electric field in the surrounding area. So how to find out this electric field? For that purpose, what I will do is at this field point, I will place a test charge. At this field point, I will place a test charge and I will find out what is the total force acting on this test charge because of this entire system of charges. And therefore, what I will do, I will keep this test charge at field point. I will apply principle of superposition. And principle of superposition typically gives me this equation. Total force acting on a test charge is a superposition of forces due to individual charges in the system of charge. So this makes your situation clear, geometry clear, and representation in the book of Griffith is clear, and the nomenclature to the point, whether it is source point or a field point. Now to find out the force acting on a charge Q, to find out the force acting on a charge Q, the very fundamental and core law that we will be using is basically a Coulomb's law. And since you are in a degree course, semester 5, basically, the Coulomb's law is introduced to you in the 11th science itself. What it says. Only thing is that in this particular presentation, we are dealing it with a vectorial notation. That is the only change in semester 5. So F bar is the force acting on test charge capital Q because of source charge small q. So what it says, this force is proportional to the product of the charges, that is small q and capital Q, inversely proportional to the square of separation between them. So this is that magnitude of position vector. Let me go back. What is this R? It is the distance between a charge and a test charge. Okay. So this is magnitude of this position vector. So square of this magnitude multiplied by this unit vector R cap. Unit vector R cap. So what is unit vector R cap? It is a unit vector in the direction of main vector. So Ri cap is a main vector which gives you the position of field point P with respect to source charge Q. And a unit vector in this direction will be the direction in which this main vector R cap R bar is basically acting, and therefore R cap is a unit vector. So F bar is acting in the direction of R cap, and R cap is acting along the direction of R bar. Fine. So it is proportional to the product of magnitude of charges. It is inversely proportional to the square of distance between them. And there is one constant which takes care of medium around. This formula is written for a free space, okay, where there is no any medium around. Basically, we call it as a vacuum. And this constant is 1 upon 4 pi epsilon 0, okay, where epsilon 0 is called as permittivity of a free space. Whenever the situation is different, like medium around is different, the value of epsilon will be different. Okay, suppose the source charges are placed in oil. Fine. So in that case, epsilon will be permittivity of the oil. Basically, it will be a permittivity of the oil. Right now, I am writing down the equation for free space. So it is permittivity of the free space in SI unit. The value of epsilon 0, okay, is something like this. And this will be its unit, Coulomb square divided by Newton into meter square. So very simple, we can find out the unit by this, through this fundamental equation itself. Product of the charges, and therefore Coulomb square will be coming somewhere. Force is there, therefore Newton will be in the picture, which is a SI unit of force, and square of the distance is there, and therefore you will find that it is m square. What is R bar? Okay, R bar minus R dash bar, which is a separation vector, that is distance between location of charge Q and location of charge capital Q. So location of charge Q and location of charge capital Q. Fine. So this is review of Coulomb's law, what we have done in our 11th science. Okay. Now let me write down our equation. The resultant force acting on a charge capital Q because of source charges Q1, Q2 up to Qn placed at various locations. So what is R1 bar? is the distance between Q1 and capital Q. What is R2 bar? Is the position vector of Q with respect to capital Q2 and so on. So I will find out F1, which is 1 upon 4 pi epsilon 0 Q1 into capital Q upon R1 square multiplied by R1 cap. This is force F1 because of charge Q1 experienced by charge capital Q. So similarly, this will be equation for F2, force due to charge Q2 bar. So this will be cumulative. This will be cumulative added together. This is basically a vector equation. Left hand side F bar is a vector. On the right hand side, every term is a vector because there is a vector quantity. R1 cap, force acting along R1 cap, R2 cap, force F2 bar is acting along R2 cap and so on. So this will be a total. I have taken capital Q, which is a common quantity outside. What remains inside is this bracket. So now what I will do, I will write down the same equation in a compact form. So left hand side is F bar, right hand side contains capital Q, so capital Q will come here. What remains entirely otherwise is something like this. So what the right hand side shows, 1 upon 4 pi epsilon 0 summation. So this is summation basically. This is a summation. It is Qi. So Q1 upon R1 square. So Q1 upon R1 square into R1 cap plus Q2 upon R2 square into R2 cap. So this is summation. This entire summation, which is a vector quantity, I represented it as capital E, okay, which is electric field capital E bar, fine. But this electric field as which point? The electric field at a field point. Okay, let us go back to see this is a field point. So electric field at field point, at point P. But where P is located? P is located explained by this position vector R bar. So electric field at point P at position vector R bar with respect to origin O. This electric field is basically produced by these source charges together. Electric field is produced by these source charges together. So this is the electric field. So electric field at position vector R bar, which is a position of field point. So what additional thing this electric field shows? That when the field point will change, R bar will change. And as R bar will change, the electric field will change. So naturally, electric field is a function of position of a field point. Let us go back. Electric field is a function of position vector R bar. That is field point. Whenever field point I will change, and if I take it here, R bar will be different, electric field will be different. So how electric field is changing in a space? How electric field is changing in a space is given by this entire equation itself. And this electric field basically depends on the source charge configuration. So where E bar is called the electric field of the source charges. Fine. So electric field is a vector quantity. This vector quantity varies from point to point and is determined by the configuration of source charges. So how source charge is distributed in a space? That determines how electric field in the space will change from point to point. Fine. I told you that this is a discrete system of charges, right? Now, what do you mean by discrete system of charges? You will find that each charge is located at a particular point. So Q1 here, Q2 here, and so on. There is no charge in between, right? And therefore, this is typically called as point charge configuration, point charge configuration, or discrete charges. Basically, in nature, many a times we come across a situation of continuous charge distribution. What do you mean by continuous charge distribution? The charge is distributed in a space continuously, and therefore you will not find any gap in between. You will never find any gap in between. Whereas you will find that there are gaps in between in case of discrete charges. In case of continuous charges, it is continuum. The charge is distributed in a continuous manner. But this is a general situation, you know. What are the typical configurations that we come across? There are three basic configurations. Okay, what are these three basic configurations? This is called as the line charge. Now, what do you mean by line charge? What do you mean by line charge? The charge is distributed. Charge is distributed along the line. Charge is distributed along the line, and therefore it is called as a line charge. This line charge is characterized by its factor lambda. It is called as linear charge density, right? Linear charge density. How we define it? How we define it? Linear charge density. Okay. So what I will do? I will divide this line of charge by small segments. By small segments. Okay. One such segment is highlighted here typically. This segment has length dl. Okay. This segment has length dl. How much charge is present on it? dq is a charge that is present on this small segment. So how we define linear charge density? So linear charge density lambda is defined as ratio of charge dq here to the length dl. So lambda is dq by dl. This lambda may be different from point to point along the line charge. It is possible. Here the density will be different. Here the density will be there. Here the density will be different. It is quite possible. Or it may be possible that this linear charge density is uniform. What it indicates? The density here, here, here along the line is same. And I will call it as uniform distribution of line charge. Uniform distribution of line charge. What is the general case? Density may change from point to point. Okay, so this is one of the configuration, possible configuration, that is line charge. Another possible configuration is surface charge. What does it mean? It indicates that the charge is distributed along the surface. So how to characterize it? What I will do? Okay, what I have done here in case of line charge, small linear segment. In case of a surface, what I will do? I will consider small surface element. This small surface element has an area dA dash. Has an area dA dash. Okay, small surface element. So this entire surface charge configuration is characterized by surface charge density sigma. Surface charge density sigma. How to characterize it? How to characterize it? Sigma will be naturally surface density of charge. So how to calculate surface density of charge? Now very simple, you know. How to calculate surface density of charge? sigma will be equal to charge here, that is dq, charge here, that is dq, divided by area dA dash. So sigma is dq divided by dA dash. Lambda is dq divided by dL dash. And now we will come to most general situation. Charge is distributed in a volume. Okay, this is three-dimensional in a volume. Fine. So what I have done? I have taken a point in this volume and a small volume surrounding to it. Small volume surrounding to it. How much is this volume? D2 dash. D2 dash. How to find out volume charge density? The logic is same. Volume charge density rho. Volume charge density rho is now what it is? It is a ratio. Ratio of what? It is a ratio of charge dq to the volume d2 dash. Okay. So this volume charge density may be, I may not say perfectly, it may be uniform. What it means? The charge is distributed uniformly in this volume. So if the charge is distributed uniformly in this volume, what will happen? Density will be same everywhere. Correct? Density will be same everywhere. Or it may possible that density will be different at different points. So it is possible. So now let me revise. Linear charge density, surface charge density, volume charge density. These are the possible configuration we typically come across. And therefore, how to represent that small charge dq? In case of linear charge, it is lambda dl. So how to understand this? What is lambda? Lambda is the ratio of dq divided by dl. And therefore, dq is equal to lambda dl. In case of surface charge, what is the situation? In case of a surface charge, it is sigma into dA dash. How to define sigma? Surface charge density. Charge dq divided by area dA dash. Okay? So charge dq is sigma into dA. Now finally volume charge density, rho. So what is charge in a small volume d2 dash? So charge in a small volume d2 dash is dq. How to write down dq? dq is equal to sigma into d2 dash. And therefore, when we will find out electric field due to these configurations, electric field due to these configurations, fine. This is a field point. Okay, this is a field point. How to find out electric field at field point due to entire line charge? Due to entire line charge, what is the practice I will do? I will divide this line into small elements. Okay, I will divide this line into small elements. Each element will be dl dash. So this element will produce electric field at field point P. Electric field at field point P. What is that electric field? That electric field will be naturally 1 upon 4 pi epsilon 0 charge divided by square of the distance multiplied by unit vector. But how this charge dq will be expressed? How this charge dq will be expressed? dq will be expressed as lambda times dl. So dq will be expressed as lambda times dl. Correct? So that is field produced by one small element. What is the field produced by entire line? Field produced by entire line is a summation of field because of all such elements together. Basically, in case of a discrete charges, this is summation. But this system is discrete because charges are separated. Q1 is separated from Q2, it's separated from Q3. But here, the charges are not separated, they are continuous. And therefore, addition of continuous terms should be replaced by integration. And therefore, you will find that this is integration. This integration is over entire line. Basically, it is a summation. So continuous summation is always replaced by integration. So sum of all the electric fields due to all elements is the final electric field at that point, field point. So this is electric field produced by line charge. What is next? The electric field because of entire surface. And therefore you will have to take integration over entire surface. Again, 1 upon 4 pi epsilon 0 multiplied by dq divided by r square multiplied by r cap. That is basic equation. But how to express dq now? How to express dq now? So dq will be here. In case of a surface charge, it is sigma dA dash. So this is sigma dA dash. That is dq. Now, what this r cap indicates? R dash indicates it is density at a point r dash. Because basically the charge is distributed over the entire surface. This is density over here, basically, density at this point, where dA dash is located. Okay? If I go to another point on the surface, density will be different. If I go to another point, again density will be different. Fine. So, density is a function of point on the surface. If the distribution is uniform, okay, if the distribution is uniform, the density rho may be same everywhere, but it may change from point to point. And what is the third configuration possible? It is a volume charge, something like this. This is a point in a volume charge. So there is a small volume around it, T2 dash. How much charge present in this T2 dash? dq. How much is the dq? dq will be the product of volume and density here. Volume and density here. And therefore it appears here as product of density into volume. So small charge dq is a product of density into volume. And that appears in this equation. Density into volume is dq. So 1 upon 4 pi epsilon 0 dq divided by r square multiplied by r cap. And therefore you will find that there is a similarity in this equation. So 1 upon 4 pi epsilon 0 common. Integration is common. Either it is line integration, surface integration, or volume integration. Okay? R square is common in the denominator. R cap is common. Only thing is that charge dq appears in a different manner in the typical equation. So this is electric field for a continuous charge distribution. So we can find out electric field due to some systems typically. So in this problem 2.2, which is explained in the book of Griffith, so I will not elaborate more on this. You might have done it even in your 11th or 12th science together, and therefore you will find that charge q is placed here. Another charge q is placed here. They are separated by distance small d. I select origin exactly at the midpoint of this system of two charges. So this distance is divided to this distance is divided. I want to find out field here. So this is a field point. Basically, this is a field point. So what happens? This charge q will produce electric field here, represented by this vector, both in magnitude and direction. This charge, again similar charge, okay? will produce its own electric field at this point, and this vector represent this electric field both in magnitude and direction. So this electric field is away from the charge. This electric field is away from the charge. Why? Because this is a positive charge. Okay, this is a positive charge. And, and therefore electric field is always away from the positive charge. And conversely, electric field is always towards the negative charge. So this electric field is away from this charge, capital small q. This electric field is away from this charge, small q. I want to find out resultant electric field at this particular point. Resultant electric field at this particular point. Okay. A very simple method I will adopt is to resolve this electric field along two directions. Either along this vertical line and along the horizontal line. You know how the vectors are to be resolved along two mutually perpendicular directions. So what are the two mutually perpendicular directions? We select one is along this direction and perpendicular. So you will find that along this perpendicular direction, the components will cancel each other. And therefore it is a horizontal components are cancelled. Why? Because component of this electric field will be along right hand direction and component of this electric field will be along left hand direction. These two electric fields are equal in magnitude basically. Why? Because electric field depends on source charge and electric field depends on the distance between the source charge and a point. These two charges are same, the distances are same, therefore magnitude of these two electric field will be same. And therefore whenever you will find out a component, right hand component here and left hand component here will cancel each other. Vertical component will not cancel, they will add to each other. And therefore it will be a summation of these two. And how this summation is expressed? Summation is expressed by this equation. So net vertical field, that is field in this direction. Net vertical field, that is field along z direction. So we are taking this as a z direction. 1 upon 4 pi epsilon 0, 2 times the field basically. Okay, 2 times the field. So 2 times. Why 2 times? Component because of this field and component because of this field will add along this direction. So 2 times. So what is this component? Electric field is 1 upon 4 pi epsilon 0 q upon this r square, upon this r square distance r square multiplied by component along vertical direction. Angle between electric field and this direction is theta. And therefore component naturally will be here multiplied by cosine of theta. So multiplied by cosine of theta. So this is total electric field along z direction. Now what they have done? They have replaced this r in terms of known quantities. What are the known quantities? This distance is d by 2, this distance is z, and therefore r square is equal to z square plus d by 2 bracket square, z square plus d by 2 bracket square, r square, and its square root will come here basically. Okay, that is r. We are putting it as r square. And cos theta also I want to substitute in terms of known quantities. So what is cos theta? Cos theta is always equal to adjacent side divided by hypotenuse, that is z divided by this r, and therefore cos theta is z divided by r. Okay, but what is r? R is given by this equation. R is given by this equation. So when I will put it entirely over here, The final equation that I will get is something like this. This we are obtaining because of principle of superposition. So total electric field here is the electric field due to first charge plus electric field due to second charge. Now if this concept is clear to you, second problem, part of the problem is obvious. Only thing, what is the difference is first charge Q is positive, second charge Q here instead is negative. And therefore electric field due to plus Q is away from the charge. Electric field due to minus Q is towards the charge. Fine. And therefore we will find the resultant of this two electric field, which will be along this axis, and this will be its electric field. One can try, very simple. This configuration is called as a dipole, two equal and opposite charges separated by some distance between them, and therefore this line that is passing through the position of charges is called as axis, while this line which is perpendicular and passing through center is called as equator. So in above situation, the field is along equator. Okay, field is along equator. While in second situation, field is along the axis. Okay, field is along the axis. So typically we call it as electric dipole. Now, when I go further, the concept will slightly change. Now, what is the typically change in this concept? What is typically a change in the concept? Till now, right from the beginning, okay, what we are attempting? We are attempting either discrete charges and a field point, principle of superposition, geometrical representation, Coulomb's law, principle of superposition and total force, then electric field due to discrete charges. Then we shifted to continuous charges, how the electric field is being represented at different points, then some numerical part. Now I am entering into the phenomena where how to represent the variation of electric field in a space, how this electric field is changing from point to point, how this electric field is changing from point to point. So for that purpose, we start with a very simple situation. What is that simple situation? This is a surface. Okay, this is a surface. So two-dimensional figure itself. Two-dimensional figure. This is a surface. Fine. On this surface, there is a point charge placed here. A point charge placed here. Okay. This point charge will produce electric field in the surrounding area. Basically, this is three-dimensional area. But to make the picture simple, what I have done, I have represented in a two-dimension. Okay, I have represented in two dimensions. This is point charge. How electric field is different at a different point? So electric field at this point represented by this vector. Okay. This field is said to be a radial field. Okay, point charge always produce a radial electric field. What do you mean by radial electric field? That at any point the electric field is along radial direction. So this is radius, this is radius, this is radius, this is radius. So these are so many radii, and you will find that electric field is acting along a radial direction. When the point is close to the source charge, okay, when the point is close to the source charge, you will find that this electric field has greater magnitude. It is along radial direction. You will find that this vector has a larger length. Okay, whenever we represent a vector according to certain unit, the length of a vector indicates its magnitude and arrow indicates its direction. So electric field at this point is greater along the radial direction. If I go to some another point like this, okay, point is away, Since point is away from the source charge, electric field is relatively smaller, of course along radial direction. If I go to next point, again further away, you will find that electric field have diminished again. And what is your observation? You will find that there is a drastic reduction in magnetism. Why this is so? It is because of the fact that electric field is proportional to square of the distance. See, denominator is square of the distance. So if the distance is low for this point, if the distance is low, electric field is large. But when I increase the distance, denominator will increase by square, and therefore quantity will reduce substantially. Again, if I go away, you will find that electric field decrease drastically. Why this is so? It is because of proportionality 1 upon r square. Proportionality 1 upon r square. Okay, fine. Let us come back. Why I am drawing this figure? I am drawing this figure to give you an information how electric field changes from point to point in a space. This is a radial field, and therefore at any point the field is along a radial direction. This field is produced by point charge. So this figure will give you a feel how electric field is changing in a space, right? It is a radial field and it decreases according to 1 upon square law. And therefore, if I go typically away from the charge, electric field will be almost very much small. Now, scientists have gone from one way of representation. This is called as a vector field. What is vector field? Vector field is a space in which every point in a space is characterized by certain vector. Characterized by certain vector. Okay? Let me repeat. Vector field is a space in which every point in a space is associated with certain vector. This is electric field, and therefore vector is electric field intensity. The word intensity is not being used by Griffith. In many other books, we'll find that the electric field is represented as intensity of electric field at a point. How intense the field is, that is how larger the field is. So naturally, for a point which is very much near, electric field is intense, okay, intense, larger. If I go away, electric field is not intense, it decreases, intensity of electric field. So this is a field, electric field, where every point is associated with electric field at that point. The same representation is replaced by another representation. What is that another representation? This representation is known as representation of field lines. Representation of a field line. So we replace vectors by line. We replace vector by line to explain the nature of the electric field. Now what is field lines? These field lines always originate from positive charge. They terminate at the negative charge. The two field lines never intersect each other. This is a representation of radial field, and therefore you will find that the field lines are radial in nature. Field lines are typically radial in nature. Okay. If a point is close to the source charge in this region, if a point is close to the source charge that is in this region, the field lines are dense. What do you mean by dense? They are typically close to each other. But if I go to the point far away like this, you will find that the field lines are not dense. The density of field lines is quite low here. You see, if I select this as an area, only 2 field lines are going. But if I select the same area here, you will find that the number of lines coming out are more. So in this area, density of field lines is more, where field is intense. Well, in this area, density of field lines is very much less, or electric field is not intense here. So intense field, density of lines is more. Not intense field, density of lines is low. And therefore, we are shifting from vector representation to field line representation. Vector representation to field line representation. This field line representation is popular both in electricity as well as magnetism. In that case, we represent magnetic field of lines, and you know that the field lines start from North Pole and that they terminate at South Pole. Whereas in case of electric field lines start from positive charge and terminate at the negative charge and terminate typically at the negative charge. Fine. So if we accept these field line concepts of representation of an electric field, the next quantity we define is called as electric flux. It's called as electric flux. Okay. What is flux then? How we typically define this word? The flux of electric field through the surface. The flux of electric field through the surface. Okay. So we should consider a certain surface. Basically, we should consider certain surface and how much flux is passing through it. How much flux is passing through it. So, how much flux is passing through surfaces? What it measures? What it measures? What it measures? So, flux measures the number of electric field lines passing through the surface S. Number of electric field lines passing through the surfaces. Okay. But how to measure them? How to measure them? So what I am supposed to do now? I must consider certain surface here. I must consider certain surface here. The surface may be open. Okay. Or surface may be closed even. Quite possible. So I consider certain surfaces which is open surface like this, for example. The way I am moving my cursor, this is my surface. How many field lines are passing through it? 1, 2 and 3. Okay, this is my surface. So 3 lines are passing through it. If I consider a surface something like this, a bit more of size, then I will find that how many lines are passing? 1, 2, 3, 4 and 5. If I consider closed surface like this, closed surface in a form of sphere, then all these lines will come out of it. So what is flux? It is a measure of number of electric field lines passing through the surface S. How to calculate it? How to calculate it? To calculate it, we use this simple equation. We use this simple equation. In this equation, what is flux? Flux is phi. It is a scalar quantity. You know, it is a scalar quantity. This scalar quantity is described as dot product or scalar product of two vectors. What are these two vectors? One is E bar and second one is dA bar. The second one is dA bar basically. What is dA bar? dA bar is small area vector. In physics, typically the word we use is infinitesimal area vector. Where this area vector is located, consider a small point and imagine a small area around it. Correct? The amount of area is dA. The amount of area is dA. How to make it a vector? dA bar. How to make it a vector? dA bar. So we define a vector quantity, dA bar. We define a vector quantity, dA bar. So what is dA bar? It is an area vector. It is always perpendicular to that area. It is always perpendicular to that area. It is always perpendicular to that area. Fine. So what is a small flux passing through dA bar? Small area dA. So small flux d phi passing through area dA. Let me repeat. Small flux d phi passing through small area dA is E bar dot dA bar. Correct? It is E bar dot dA bar. Now this will explain to you one more definition of electric field. One more definition of electric field. How we define a new definition of electric field? E bar at any point is a ratio of flux d phi to area dA. So how to define electric field? Electric field is d phi divided by dA. If the flux is normal, the flux is normal. So electric field is density of flux. Is density of flux. Electric field is d phi divided by dA. What is d phi? Small flux. What is dA? Small area. So if d phi by dA is more, electric field will be more. Correct? So when this d phi by dA will be more, when this d phi by dA will be more, it will be more when d phi is more. That is, number of lines are more. Let us go to this particular figure. If I consider area close, density of flux is more, electric field will be more. If I take the same area very much away, if I take same area very much away, density of flux, that is number of lines of force passing to unit area, density is less, electric field will be feeble, that is low electric field. Correct? So new definition of electric field in terms of flux is that electric field intensity is normal flux density, is normal flux density. Electric field previously we have defined in terms of this equation, electric field, in terms of force between the two charges. And now I am defining electric field in terms of flux. So therefore there are two versions to look to the definition of electric field. One is vector version and another is field lines version. Correct? So here the electric field is expressed in terms of density of flux. And therefore how much is the flux through entire surface S? How much is the flux through entire surface S? The flux through entire surface S is a surface integral of such small fluxes passing through individual small area dA. Correct? So this is basically d phi. flux passing through small area dA, and its continuous summation, which is replaced by integration. Continuous summation, which is replaced by integration, will give you total flux passing through total area S. Total flux passing through total area S. So this is a fundamental concept. Flux is a scalar quantity because it is derived as a scalar product of two vector quantities. Scalar product of two vector quantities. And what flux? It is a measure of number of electric field lines passing through surface S. So we have gone through certain definition of a flux. So either calling it as flux, in a mathematical terminology, let us call it as a surface integral. Okay, instead of calling is a flux, we call it as a surface integral. And this flux of which vector? Flux of which vector? Flux of vector E bar. Fine, let us go back. It is a flux of vector E bar. It is a flux of vector V bar. So flux of vector E bar is this surface integral. Okay. Now this flux is passing through sphere of radius R. Okay. What does it mean? That we imagine a sphere like this. Now sphere is what type of surface? Is it open or closed? Sphere is a closed surface. And through this spherical surface, the lines are coming out. And total number of lines coming out is called as flux. Correct? Number of electric lines coming out is called as flux. So we are imagining a closed surface. Correct? So we are imagining a closed surface spherical of radius R. And this flux is obtained as a surface integral. How to numerically calculate this surface integral? The formula is very much clear. It is a vector product of E bar and area vector dA bar. Find out this vector product. Take its integration over entire surface. Now, if the surface is closed.
Hello, sir.
Hello.
सर सॉरी तुम्हाला मध्ये थांबवतोय.
हा,
आपला
हा.
2 वर्षाचा दुसरा लेक्चर आहे सर, तो
बरोबर.
आपल्याला चालू करावा लागेल.
बरोबर.
रिक्वेस्ट करतोय तुम्ही इथंच थांबला तर बरं होईल.
हा, चालेल. पण मग मला असं आणखीन मिळणार का संधी? काय सिच्युएशन आहे की इथे थांबूया?
हो पुन्हा तुम्हाला
चालेल.
थांबा.
आपण काय करू, एवढी स्लाइड मी संपवतो की इथेच थांबूया. गॉस इथपर्यंत थांबूया. या पॉइंटला मी थांबतो. हा, ओके, फाईन.
इथेच थांबा सर.
ओके, मी स्टॉप शेअर कसं करू का? स्टॉप शेअर करतो मी आता. हा.